talk about, last time we were stuck at basically what is jump. I thought about it when I went home actually. So we were kind of differentiating this function x y equal to x plus. So after the map from R to R. Okay. And then we evaluated f of a plus h, minus f of a, where a is vector a1, a2, and h is an arbitrary vector. So it's a fixed vector and this is an arbitrary vector h1 and h2. So this becomes what? This would be a1 plus h1 by definition plus a2 plus h2, right? And minus f of a into a1, a2. And then we did a1 h2 plus a2 h1 and h1 h2. So this was something that we did last time. Okay. So then we were kind of thinking and pondering that we took this as something linear and we took this as something irrational.
Yes.
The question is why we are not taking the derivative. The answer is pretty trivial. Okay? This is non-linear thing actually, because it's a product of two numbers. So product of two, what do you call variables. So is xy is linear? Is xy linear? So what is the degree of this? 2. Okay? So this can't be for sure derivative of that, what do you call, linear approximation, because this is non-linear term actually, while this is linear term. Why this is linear term? Because a1 and a2 are fixed numbers.
So
the degree is 1 actually. So we have no other choice except saying that this is my L of h and I should treat this as the error actually. This is kind of a more satisfactory explanation actually then.
Sir, will you not feel such type of things in other problems in which we have not the polynomial function, but we have other functions like sine and trigonometric functions? Will we not feel difficulty in selecting the error and other terms?
No, we will not actually, because today we are going to prove something. After that, you will say the easiest thing to compute in the world is the Frechet derivative. You don't have to go for the definition. It's like you don't apply, for example, in one variable calculus we have did it, that you don't apply the definition. So theoretically it is possible, but you don't apply definition of the limit onto something very complicated function, because you know that it's going to be more messier actually. So when you want to learn to do the derivative by definition, you take simple functions. Let's take sine x or maybe x power n and something simple actually that you can give, right? So similarly, we are learning how to differentiate, but through simple examples. Okay? So why I am taking this as a and this as linear operator, because this is the linear part. So it doesn't make sense to take this as something linear. Okay? And then we can really show that if you divide it by the magnitude, then the error will go, error divided by the magnitude of h will go to the 0, and this is the Frechet derivative. Okay, the Frechet derivative when operated on the h. Okay, that's what it is. So I hope this is a good explanation. So another indication to know that actually which thing should be the Frechet derivative and which thing should be the error. So think about the linear things actually. Put together all linear things and that will be the Frechet derivative. Can you see why this is linear? Again I'm asking. Because a1 and a2 are fixed numbers, where h1 and h2 are arbitrary. Okay? So this has a degree 2 while this expression has degree 1. Okay, so I hope this is sorted out now. So what we would like to do next is to prove some of and to talk about some of interesting kind of propositions actually. Okay, so for example, we know that total derivative is doing what when you are sitting at a point on a function or a surface is basically giving you the change in all possible directions actually, giving you more than that. But out of all those directions, now we will like to talk about, okay, using the Frechet derivative, can I compute the change in my selected direction actually? So we have lots of directions in which we can compute the derivatives. So the total derivative is giving you change in all directions. But can it give me, can I restrict it in such a way that it gives me the change in the direction of my particular choice? The answer is yes actually. Okay? So let's take this to a new level. So I would like to talk about some more. So this is one objective that we're going to cover today. Let's see how much part we can cover. So let's begin with path and the tangent vector, and let's see some of the properties of such kind of Frechet derivative for the paths actually. So what do I mean by path? So the path means that imagine I have a particle and the particle is moving in free space, and the path traced by the particle is basically going to be a curve. We have a curve, okay? And okay. So I'm going to denote. So maybe the particle is moving for a certain amount of time. Okay, so this is the time for which the particle is moving actually, and this is the path that traced. Okay. So in other words, for each instant t naught, I can trace a position onto the particle, onto this curve here. So if t is an arbitrary point, then I can have a p of t here actually. So, okay. So by a path, mathematically, I'm gonna mean a map, okay, p from the interval I into something that is in Rn actually. Okay, so this is sitting in R3, so something that is in Rn. Okay, so more precisely you can have, so this is the timeline, and you have three-dimensional space, and each point of timeline you are mapping onto some point of three-dimensional space, and when you combine all these points, the outputs of all these points, you get a curve actually, so you get a space curve. Okay, and you can call that curve, curve is a technical term, we will define it later, but you can call it a path actually. Okay, and we may interpret this path as the path traced by a particle that is moving in space. Okay, but mathematically, so path is what? It's a map from an interval I into the space Rn, where P is a continuous map. Okay, so a continuous map from the interval I into the space Rn is what you call is the path. Okay. And we know that roughly what I am saying, that imagine this line is like something flexible. So the global picture you can this mean. So imagine this line is made up of something rubber actually. So what you are doing, you are taking this out and applying some transformation over it, and becomes a curve in space actually. Okay. Okay. So in other words, I have for example, wire, which is one-dimensional, okay, but I can twist and turn that wire and make a curve out of it. Okay, so what I am doing is that I am essentially taking an interval, a bunch of things, and applying a continuous transformation over it and making it turning into a curve actually. Okay, you can have different interpretations. All these are interpretations actually. Okay. So you call such kind of a continuous map or a continuous transformation of I into Rn a path actually. So path is such kind of a map. Okay? So it's a path traced by a particle. So if it is a path traced by a particle, what immediate questions you can ask about it? So P of t, okay, so if the t is the instant, P of t is the position of the particle at the time t actually. Okay? So what other questions you can ask about this particle?
This rate to move the
So you can write what is the velocity of the particle. right? What is the speed of the particle? So if you are interested in finding the velocity of the particle, you need to do what? You need to do the differentiation actually. But which differentiation we have in Rn? We have the Frechet derivative. So let's try to compute the Frechet derivative of the path actually. Okay? So in general, path is going to look like what? So it's going to swallow an instant t and give me a vector in Rn, which is going to have some components. So let's call those components p1 of t, p2 of t, and say pn of t. Okay? Where these pi's are what? So these pi's are the maps from I into R. Okay? So these are numbers. Okay? So these are the maps from I into R. I hope you must have learned some geometry. Did you learn some geometry during 3D geometry, a little bit of 3D geometry in your calculus 2 course?
Geometry, sir. We had geometry, sometimes polar curves are like this type of curves.
You did some of this.
Yes.
So what would be one example of this actually? So one example of this could be, say, if I say my P of t is the same, say what? Okay. 1 and 1 p and t. So what does this would be? So this would be equation of a. So it's a line. Okay. So it's a straight line. How can I see that this is a straight line? So what is the meaning of being 1 at position? So maybe the line, so if this is the value 1, so it should pass through. So you have a line which is in what? YZ plane, okay? But it is stuck at 1. Okay, so it could be what? So what would be the so how does this is going to be? So it's t to 2t. So z is the 2 times of the t. So it's like a y equal to 2x equation actually. Okay, so it's going to be some kind of a it's going to be a line actually. Okay? You can plot it and have the picture. Okay, so it's a straight line. So that's one part of the example. We'll talk more about it in the next chapter. The next chapter is all about curves. So I would like to just talk about a little bit of properties of it actually. Say for example, if you take P of t to be what? Say cos t, sin t, and t. What this would be? So it would be circle if t is fixed. If t is 0 or 1, then it's a circle actually. So in other words, so if I put for example 1, what does this mean? That at z I have a circle actually attached to it environment plane actually. Okay, but so this is not 1 or 2 or 3. Okay, so it's p actually. So you see it would be a helix actually.
Yes.
So it would be a helix actually. Okay? It would be a helix with that's a circular helix actually. So you can visualize it. This is an example of a circular helix. Okay, so if a particle is moving in this manner, that means it's moving on a helix. Okay, so maybe you are that particle and you are moving on Masoom Shah Minara actually. Yes. Think about it. You have to move in this manner. Try to reach at the top actually. Isn't it? Or maybe you are coming from the, it's not really helix, but it's something similar. You are coming from the ground floor to this floor. So how you are moving. It's not a perfect helix, but, okay. Are you getting the point?
Yes.
Almost like a helix.
What's different between spring and helix? Spring is also like this.
It's an example of a helix, yes.
Helix.
It's an example of a circular helix. Okay. Anyway, ठीक है जी.
सर ये जो पाथ है ये वन डायमेंशनल होगा?
It's a one-dimensional object sitting in. Okay. So curve is one-dimensional, but sitting in three-dimensional. So therefore, you call it a space curve actually. So in other words, it's one-dimensional. What do you mean by dimension? So you don't. So to describe a point on a curve, you only need a point T actually. So you just need a T. So it's just one point. So therefore, you call it as a one-dimensional thing actually, for example. Okay, but its graph is not going to be one-dimensional. It's going to be three-dimensional. So it's a helix which is one-dimensional but sitting in three-dimensional actually. So the ambient dimension is 3. Okay. You will mostly talk about such things in the differential geometry course actually. So these are just two examples. It's a line, helix. If I fix a number, you will have a circle stuck at a point in the axis. You can plot it. So, question. If I take, so that's a vector valued function, isn't it? It's a vector valued function, and we know how to differentiate a vector valued function. So in other words, if you want to compute, the Frechet derivative of the path evaluated at a point h. Okay. By the way, what would be the description of the Frechet derivative of a path actually? So the path is a map from I to R, right, to Rn. This derivative would be mapped from where to where? It will be again a map from I to Rn, R to Rn. Okay. So if it is a map from R to Rn, so here h is not a vector, that's a number actually. So that's a number, no, it's not a vector. Okay. You always need to realize that what we are talking about. So if you want to compute it, how can I compute it? So just compute the Frechet derivative of each component and evaluate it at h. Right? Now each component is a one-dimensional object, so it's a map from R to R. Okay? So in one dimension, so for the maps from R to R, what is Frechet derivative? It's simple derivative, it's ordinary derivative actually. So if it is ordinary derivative, what does it mean? So I have a p1 prime of t, so it's a simple time derivative, okay, operated onto h, but operated onto h means multiplied with h, okay, and up to pn prime of t, okay. So h is like a number, it's a scalar in each component, so if I wish I can pull it out, okay. And so you're going to have p1 prime up to pn prime. And if I wish, I can write this as p prime of the t times h actually. P prime of t is what? So it's p1 prime, p2 prime, so it's like differentiating each component with respect to time and multiplying that. So this would be the Frechet derivative of it. Okay? So what would be the Frechet derivative of this guy? P of t. So this would be 0, 1, and 2 actually. Okay, 0, 1, 2. So fix. Okay, so in other words, and it makes sense actually. So if a particle is moving on a straight line, okay, so you expect it to have a uniform kind of a motion. Yeah. But such kind of particle is, if a particle is moving, in the form of a straight line, that means that it has what you call, its motion is uniform. Okay, so it's at a constant velocity. No acceleration. No acceleration. ठीक है? Okay. If I substitute 1 here on the place of h, so I can say basically p prime of t is nothing, is just compute the Frechet derivative of the the path and evaluate what? 1 into the dimension. Okay. So p prime of t can be written as, what do you mean by that? So the good thing about this is that the Frechet derivative evaluated at 1 is giving you a vector derivative actually. A derivative of the vector with respect to the time. So in other words, this is not something exclusively new. The Frechet derivative contains this information actually. Frechet derivative is something that can become, the vector derivative as well actually, the derivative of the vector with respect to the time t, a single parameter derivative. Okay, समझ आ रही है? So I'm moving towards a point, and I'll make you realize again and again and again that if a function is differentiable at a point, then Frechet derivative contains the all information about the all kind of derivatives actually. So it can give you derivative of the vector, it can give you directional derivative, it can even give you partial derivatives actually. So partial derivative and directional derivative and such kind of derivative are the examples of the Frechet derivative. Are the Frechet derivative computed in a certain fixed direction? They are particular manifestation of it. ठीक है? समझ आ रही है ना? जैसे kid and boy and male and female and all these are the manifestations of the human. So the human is a generic word actually. The gene is human. ठीक है? बाकी सब manifestations हैं इसकी. So Frechet derivative is something like similar. So it's general. ठीक है? बाकी छोटे-मोटे जो derivative आप पढ़ेंगे, you will see that these are just manifestations of the Frechet derivative. ठीक है? Is it making sense? चलो. So one example we already did, so we can have it. So now let's talk about one very interesting property of the Frechet derivative, but before that I need to define what do we mean by having a velocity of the particle. So if I interpret the path as the path traced by a particle, okay, that is moving in space, then what would be the meaning of velocity? So how do you define velocity actually? So if p of t is representing the position of the particle at the time t, how do you define derivative actually? Okay, so what you're going to say that, okay, define what we call tangent vectors. Okay, so suppose that 0 is in I. Okay. And p of 0 is a. To motivate you where we are heading in the next part of discussion is this. Imagine I have a curve, okay, and I apply some continuous transformation over it. So imagine I have a curve. Does anyone have headphones actually? Okay? Yes. Headphones, huh? Yes, you have. A lot of sound of the music actually. Yeah? So you have headphones. So imagine I have this curve actually. So I already have this curve. That's one curve. That's one space curve. Huh? So I have this space curve. So what I'm doing, I'm applying a continuous transformation over this curve. So imagine I'm turning it into something else. That's a new curve actually. Okay, so I applied a continuous transformation and turned it into a new curve. Okay. So what I would like to prove that if you take this curve, okay, and take a point and take a tangent vector over it, okay, and take this curve, okay, this curve, which is a transformed curve, okay, under continuous transformation. Why I am saying that this is a continuous image of this curve is because that I am not breaking anything actually, so I am not digging any hole. So topologically they are same. Huh? So if I have a tangent vector over this curve, okay, and I have, so if I transform this into a new curve, the tangent vector would also transform actually. Okay. So what the Frechet derivative is doing, okay, is gonna take this, so tangent vector on this curve, okay, and is going to map it onto the tangent vector on. So if you want to find the tangent vector on the transformed curve, so do one thing, find the tangent vector here and substitute it into the Frechet derivative. You're gonna get the, the tangent vector onto this transformed curve. Okay. So ek aur, what do you call, the interesting thing the Frechet derivative is doing. So it's like, it's a tangent gun actually. So the mapping tangents onto the tangents, huh? Something like that. So if you insert tangents, it throws out tangents actually. Anyway, so that's what we like to do. So therefore we need to define tangents and all that. So that's what, so I would like to, put it into a form of a theorem, this observation that I just told you actually. Okay, so imagine 0 is inside the interval, at any point, and so when I'll operate the p onto the 0 is going to be a point on the curve. So if this is a curve, then this guy is what do you call the point A, and let's call it, this is p of 0. Okay. So if you want to draw a tangent at this point, so what do you need to do? You need to differentiate the curve, okay, and substitute 0 into it. So the p prime of 0 is going to be tangent vector x. So if the p of 0 is the point A, then p prime of 0 is going to be the tangent vector to the curve. Okay, so it's gonna, you can interpret p prime of 0 as the velocity of the particle actually. Okay, and then you can also interpret p prime of 0's magnitude as what we call the speed of the curve. Okay. But you can also define it at an arbitrary point. So in other words, p prime of t in general is the tangent, the velocity of the particle at any time t, and its magnitude is the speed of the curve. Okay. Now imagine f is a map. So imagine I have such kind of a curve and a tangent vector over it. And imagine now I'm taking a map, f from Rn to Rm, and I'm doing what? I am, so if f is a map from Rn to Rm, and this is a curve in Rn, because p is a map from where to where? So p is a map from I into Rn actually, okay? So p of t, at an arbitrary point is a point in Rn, okay? So this is p of t, so the graph of the p of t actually, okay? So if f is a map from Rn to Rm, and if assume f is continuous, so it's not only continuous but and differentiable, at least at this point, and differentiable at Rm, okay? Then what would be f composition p? So the f composition p is going to be a map from I into Rm, okay? So in other words, that's I, okay? That's straight is I, and that's what do you call p of t, the path. And then on this path, I'm doing what? I'm applying a continuous transformation, so it turns into a new path actually. So it's turned into a new path, okay? So you can visualize it as f is a continuous and differentiable at a point p, then f composition p is a map from not Rn to Rm, but Rn to Rm actually, okay? So you have this kind of a situation. So you have this curve, so that's p of t, okay? And the point A where you have p of 0, and I'm taking this path and transforming it. So what would be the f of p of t? Okay. So what would be f of p of t? In other words, what would be the f composition p operated onto t? So it is going to be a new curve. I don't know how does it look like. So maybe it looks like this actually, something like that. But it should be a continuous transformation. Are you getting the point? Okay. So at this point A, I can have a tangent vector. So this is p prime of 0. So this point A would also be transformed under f onto this path actually. So where would be that path? I don't know, maybe it's here actually. Okay. So the f of A, so this is b equal to f of A, or you can also treat this as so if you see from the path point of view, then this is p of 0, then you have f composition p of 0 actually. Okay? So the f composition p of 0 is b, you can also treat it as f of A actually. So you're going to have tangent vector here as well. And what would be that tangent vectors if you would like to describe it? So it's going to be f composition p. So compose it
It's a derivative.
and compute derivate and evaluate 0 into it. So that will be the tangent vector at the point 0 actually. So what essentially I am saying, take a table, make a curve out of it, take a continuous transformation and transform the path into a new path actually. And you're going to have a tangent vector here, and you're also going to have a tangent